Now that we've covered an introduction to motion, we're going to be diving into Newton's laws. We alluded to them briefly as we covered motion when we talked about how accelerations are caused by forces, and so Newton's laws get into how those forces behave. You've had these before, of course, but we're going to go a little bit more in depth than you have in the past, and we're going to bring in the math. So, diving in, there's Sir Isaac Newton himself, and his first law of motion says that an object at rest wants to stay at rest, while an object in motion wants to stay in motion. There's a little caveat there, in a straight line. So it doesn't want to just move, but it wants to move in a straight line, unless it's acted upon by an outside force. Or another way of stating that is an object will continue doing its current state of motion, whether that's moving or at rest, unless acted on by an outside force. Newton didn't come up with this one totally on his own. There's a famous quote of his that says that if he's seen further, it's only by standing on the shoulders of giants. And he based this off of Galileo Galilei's observations of this. And both of them together had the insight of imagining frictionless surfaces and air resistance free areas, that objects would move in the absence of friction and in the absence of air resistance and just keep going forever. Prior to that, Aristotle, a few thousand years beforehand, had said that for an object to move, it had to keep being pushed. And so for an example, an arrow flying through the air would get out of the way, come around behind, and keep pushing it forward. And so then you had to constantly push to keep an object in motion. Well, what Galileo realized and Einstein kind of expanded upon was that if we don't have friction, if we don't have air resistance, the objects will move forever. And that the reason that normal objects, everyday objects, eventually come to a stop is because there is this outside force acting on them. This law is also known as the law of inertia, which we're going to get into some of extra details before we continue with Newton's laws here. So inertia is simply the tendency of an object to maintain its current state of motion. It's how likely it is to keep doing what it's going to do. And inertia is related to mass. So the mass of an object is the amount of stuff that makes it up. Remember that all matter has mass and volume, and so the more mass you have, the harder it is to convince you to move, and once we do convince you to move, the harder it is to get you to stop. And so mass is essentially a measurement of inertia. And although the metric base, which we covered a long while ago for mass, is grams, they tend to be too tiny. So in physics, we tend to use kilograms. In fact, some will say that physics use the MKS system, meters, kilograms, and seconds, because rather than using grams, we use kilograms. Weight is different than mass. And so you are still made up of stuff if you go into space. And so we talk about you being weightless in space, and really it's that you're constantly free falling, you just don't feel the effects of gravity, but you still have mass in space. You're still made up of stuff. And so the best weight loss program there is to just go into space and you lose all your weight. But what people really mean is a mass loss. Now here on Earth, if you don't leave Earth, it doesn't really matter which one you use, mass or weight. But in the English system, when we use pounds, that is a weight. It's not actually our unit for mass, which, again, we covered way back when we covered the metric system. Weight is simply the force of gravity acting on an object, and on the next slide, we're going to get into the formula, so we'll touch on the units there. But pounds is a weight and not a mass, and so although we'll sometimes talk about converting kilograms to pounds, it's not the proper thing to do because we're turning mass into weight. Anyway, this brings us to Newton's second law of motion. Newton's second law of motion is really wordy, and other than getting the fact that we abbreviate force with an F here, it's better to just dive straight into the formula, because Newton's second law of motion is really a formula, or a description of a formula, and it says that force is equal to mass times acceleration, or abbreviated F is equal to ma. Now, masses are measured in kilograms, and accelerations are in meters per second squared, so the units come out to be kilogram meters per second squared. That gets to be a little bit of a mouthful, a little wordy, and so what we do instead is we have a combined unit, an abbreviated unit, which we call Newton. And here we see a capitalized abbreviation. Anytime a unit in the metric system is named after a person, we use a capital letter for the unit because it's their last name. And although you should have newtons. I will accept kilogram meters per second squared, and the downside is if you're doing the thing where you have to check your units, or if you're using the F equals ma formula to not solve for force, which is in newtons, but to solve for one of the other values here, you really need to know in the back of your head that the units for it are kilogram meters per second squared, so that you can cancel out your units properly and figure out what your units for the mass and acceleration are. As I mentioned a moment ago on the prior slide, there is the special case of force called weight, and for that we abbreviate force with an F subscript g instead, just to emphasize what force it is. And for the special case of weight, it's mass times the acceleration due to gravity, and acceleration due to gravity is abbreviated with a lowercase g. And g is a constant. It's kind of like pi, which you have had in math before, where pi is equal to 3.14159, and that is a universal constant. It's true everywhere. But for g, it's only a constant here on Earth, and it always has the value of 10 meters per second squared. Now, it turns out that's actually a rounded value, and the true value of it is 9.81 meters per second squared, and it does vary a little bit depending on where on Earth you are, but we're going to go with the simple math and just round that 9.81 up to 10 meters per second squared. If you take physics with me, we use a more precise value. But the acceleration due to gravity on Earth is 10 meters per second squared. Later on, you'll get a separate video where I work through some example calculations, and you'll find that frequently you'll be given a weight of an object, and you'll have to use the force of gravity calculation here to solve for the mass, so that you can then take that mass and plug it into the F equals ma calculation. We're not going to get into it this year, but if you go on to take physics with me, we have all sorts of other formulas that calculate forces, and frequently what we do is we replace the force on one side of the equation with ma, and we use it F equals ma all the time. And remember, forces cause objects to accelerate. That is to change their current state of motion, and accelerations change velocities, and velocities, remember, have two pieces. They have a speed and a direction. And so accelerations can be changing one or both of those, and accelerations can change one or both of those. This now brings us to Newton's third law of motion. For every action, there is an equal and opposite reaction. And I have to be honest, I remember this being taught to me when I was in late elementary, and I remember thinking, how in the world can something be equal, the same, and yet also opposite? And it was never well explained, but I want to make sure that you have a clear understanding of this. So when we say equal, what we mean is equal in magnitude, equal in size, equal in the amount of force, and opposite in direction. And so when you have two objects interacting, or two things interacting, the forces have to be equal in size and opposite in direction. Right now I'm sitting on a chair, and gravity is pulling me down into that chair by an amount equal to my weight. The chair then, on the other hand, has to be pushing up equal amount, my weight, and again, we've already said direction here, up, for me to stay at rest, for me to maintain my current state of motion. And so, equal in size, opposite in direction. And something I want to emphasize there, it's always in the form of object A, say me, acted on object B, the chair, and the reaction is object B, the chair, acting on object A, me. And so it's always one acting on the other. This will matter later on when we get into doing force diagrams, because a lot of times we'll have a pair of forces on an object that happen to be equal, happen to be opposite, but because they're both acting on just one object, say on me, then it's no longer a equal and opposite reaction. It's a coincidence, essentially, that it's that way. So, for example, the forces acting on me right now are the chair pushing up and gravity pulling down. Well, gravity pulling me down is the Earth and me, and the chair pushing up is the chair and me. So I have a pair of forces acting on me that happen to be equal and opposite, but they are not a action-reaction pair. Action-reaction pairs are always object A acts on object B, and object B acts in an equal size opposite direction on object A. And although we talk about them being action and reaction, it is instantaneous, it is simultaneously, they occur at the same time. The moment I sit on my chair, the chair begins pushing back. shrink. And as I'm lowering myself and pushing more and more and more on the chair starts pushing more and more and more on me. If the chair can't do that, then I might say break the chair. And then at that point, we have unbalanced forces on me, and we get into the realm of Newton's second law, where I'm going to begin to accelerate down because I have a net force on me now, which comes from the first law. And that brings me to this final slide here, and that is, although we'll talk about situations like this is a good example of the first law, or this is a good example of the third law, all three laws are going on all the time. All three always apply and always matter, and they are universal laws. They are true everywhere in the universe. Newton's three laws of motion all going on all at the same time. So the first law is the law of inertia, the second law is F equals ma, the third law is our law of equal and opposite actions and reactions, and then from there we have these relationships. It turns out that with the first and second law, when you have no net force, then you're maintaining your current state of motion. This gets into something that we're not going to cover this year, but impulses and momentums, and those are the formulas for them there. And the third law relates to the second law in that we can calculate the F equals ma for both objects, and they're equal in size, but opposite in direction. Remember, signs can indicate our direction. But all three are always going on everywhere all the time. We'll do another video about forces and force diagrams, and we'll also do a video on practice calculations and practice force diagrams so you can get used to how to do these before you get set on homework over these. Anyway, be sure if you have any questions that you let me know.